Okay, so we've just finished our initial study of speed and velocity and distance and displacement, and this video is going to focus on acceleration, or the rate at which things are speeding up and slowing down. Okay, now in real life, speed and velocity are very rarely constant. Okay, so we need a way to quantify the rate at which speed and velocity change. Okay, now if there's a change in speed or a change in velocity, and remember there can be a change in velocity without there being a change in speed, remember that. Okay, anyway, if either of them are changing, there's going to be an acceleration. Okay, velocity is a vector, and it turns out that acceleration has to be a vector because acceleration can be positive or negative. So in this particular case, here's this jet airplane, maybe a Blue Angel, taking off. It's going from left to right in this diagram. You can see that its final velocity, which is given by v, is greater than its initial velocity, which is given by v naught. And we know that because this vector is quite a bit longer than that vector. Now, this delta velocity, this change in velocity, would be the final velocity minus the initial velocity, or v minus v naught. And the acceleration would be that change in velocity over the time frame in which that velocity changed. So in this case, my delta t would be t minus t naught. So you can see that at a later time t, it was going at velocity v. Turns out that in this case, the jet is speeding up, so its acceleration would be in the positive direction. Okay, and here's a video of a jet speeding up on an aircraft carrier. We have a really significant, huge accelerations of jets like this. Okay, so that's a lot of meters per second that the speed, the velocity of that jet is actually increasing. Okay, and that leads me to my discussion of the equation for acceleration, which is change in velocity over change in time. It's a vector, and the SI units are meters per second per second. So another way to think about it is that the meters per second change in velocity per second of time. That's where we get a second squared on the bottom. Okay, now in this class, we mostly deal with constant acceleration. So there's no need to worry usually about instantaneous versus average. We do deal with circular motion where there's a constant acceleration, but with the exception of circular motion, we deal with acceleration in a straight line, make things easier. So acceleration can be positive or negative, forwards or backwards, and this is called uniformly accelerated motion in the IB. Okay? All right. Now, if my change in velocity is positive, then my acceleration is positive. If my change in velocity is negative, the acceleration is negative. Now in the IB, we refer to initial velocity as u and the final velocity as v usually, okay? So this means that acceleration then becomes v minus u because it's the final state minus the initial state, always gives the change in some quantity divided by t minus t naught. Now, as I said before, if the change in velocity is positive, the acceleration is positive. If the change in velocity is negative, then the acceleration is negative. We don't have to worry about delta t being negative because time can't go backwards, right? So tf is always greater than your t naught, okay? Now, rearranging things, we come up with this equation right here. Okay, and this is what's given to you in your data booklet. And notice correctly that if acceleration is 0, then v equals u, in which case the final velocity and the initial velocity are the same. Okay, and then your time term doesn't matter at all because it's just multiplied by 0. I just want to remind you of a previous slide that we saw before where we derived this equation. And pause the video if you need to go over this again. I'm not going to go over it in detail, but we derived this equation for the displacement of a moving object. Okay, so S equals S naught plus Vt, where V is the velocity, S naught was its initial displacement, and we noted at the time that if the velocity was 0, then the final displacement equals the initial displacement, which makes complete sense because it means that the object is not moving, so it just stays where it started. Okay, I want you to think very carefully about the obvious analogy between these two equations. Okay, same form, right? We derive them in a very similar way, and I also want you to start thinking about what these equations would look like if you graphed them, and especially considering they're sort of, if you look at it carefully, they're sort of in the form of y equals mx plus b. Okay, so that being revealed to you, I want you to think about what would be the slope and what would be your y variable, your x variable, and your y-intercept. Very interesting. We'll come back to all that later, but you should start thinking about that now. Okay? All right, now in this video we have this big massive truck. that's coming to a stop very quickly from a high velocity to a zero velocity before it rear ends this sort of test car, okay? And I want to show you, I want to give you an idea of sort of what the vectors would look like that I've been talking about here. Now, with the exception of the final spot where t equals tf, the velocity is always to the right in this case. Well, the change in velocity is always to the left in this case, right? Okay, because because the velocity vector, when the truck is going very fast approaching the car from a distance, the velocity vector is very long, okay? It gets shorter and shorter and shorter until it becomes zero, okay? But everywhere the velocity vector is pointing to the right, so it's positive velocity. My change in velocity is always to the left, okay? And I'll talk about this a little more in class if you guys remind me. I can show you visually how that delta v is always to the left. Because the rule is that A points in the same direction as delta V, this means that my A is to the left, so it's actually a negative acceleration, okay? So we need to be really careful keeping track of all of our signs, okay? And in the next slide, I'll talk a little bit more about that. And I just want to remind you that the value of the acceleration depends also on the time frame. Delta V and A always point in the same direction, okay? All right, so I'm going to go through a couple of different scenarios here. We're going to sort of go through and figure out how delta V and A and V and U are all related in terms of vectors and direction, okay? So I'm going to show you a series of diagrams depicting what could be like a bowling ball rolling, okay? So in this first one, in the very top diagram, you can see that the bowling ball is speeding up. It's going at t equals 0. It's going from 2 meters per second all the way up to 6 meters per second at t equals 2 seconds. So clearly it's speeding up, okay? In the bottom case, it's slowing down. It's going from 12 to 4. Now in the top case, I'm computing my delta v, and for clarity, I'm using v sub f to be v and v sub I to be u, okay? So v sub f is your final velocity, v sub I is your initial velocity, okay? The change in v in this case would be positive 4 meters per second, okay? Positive 4 meters per second. So what does that mean? That means that the acceleration is going to be positive. In the bottom, delta v is negative 8 meters per second. Just work out the numbers, right? 4 minus 12 is negative 8. So in this case, and remember, I haven't pointed out something really important. You're probably wondering. You always show the acceleration vector with 2 arrowheads to differentiate it from the force from a force vector. Okay, I think I mentioned that before. Not sure. Anyway, that's what this vector means with the 2 arrowheads. In this case, I have a positive delta v. I just calculated that right here. So, and everywhere there's a positive v, right? Okay. Because there's a positive delta v, I also have a positive delta a in this case. Now, in the bottom case, I also have a positive v, all right, for all 3 of these because it's moving to the right. But now I have a negative delta v, which is actually twice the length. This vector is twice the length of this one up here, so I have a negative acceleration, okay? In the next case, now we're going from right to left, okay? So at t equals 0, I have negative 20 meters per second. At t equals 2, I have negative 10. The ball is slowing down, but in the negative direction. Does that make sense? So the speed was greater at t equals 0 here than it was at t equals 2. Okay? On the bottom, the ball is speeding up, but in the negative direction. At 0, the speed is 5 meters per second, and at 2, it's 11 meters per second. Now, in the upper case, delta v is positive 10 meters per second, and in the lower case, delta v is negative 6 meters per second. So what does that mean in the top case? It means that you have a positive acceleration, and the positive acceleration in this case is serving to slow the ball down because the ball is moving in a negative direction. You want to really think about that for a minute if you're not getting it, okay? In the bottom case, the ball is speeding up, but we have a negative acceleration because the ball is already going in the negative direction, okay? So really important that you differentiate between these 2 cases, okay? The third case gets even more possibly complicated, okay? What's going on in the third case? Well, in the upper diagram here, the bowling ball started off at t equals 0 going negative 10 meters per second. At t equals 2 seconds, it ended up going a negative 20 meters per second, so obviously it's speeding up. Notice how it's being depicted a slightly different way here, where my earlier time is on the left and my later time is on the right, okay? In this case, Delta V is again negative 10 meters per second. This is somewhat like the bottom diagram over here, okay? And I have that there's a negative delta V, so negative A. So that is correct in this case. It's speeding up, right? Okay, because the ball's always going in the negative direction anyway. In the bottom, my delta V is a positive 6 meters per second, which means that I have a positive delta V and a positive A, okay? Even though the velocity is negative, the ball is actually slowing down. So you really want to take some time, pause the video, and really study this slide if this stuff is not making sense to you right now, okay? Really important. Okay. All right, here's an example that you should, I want you to work out before I do it for you. It's a fairly easy one. Okay, so a drag racer crosses the finish line and the driver deploys a parachute and applies the brakes to slow down. As shown, the driver begins slowing down at t equals 9 seconds when the vehicle is positive 28 meters per second. Okay, now 3 seconds later, the velocity is positive 13 meters per second with the acceleration of the dragster. Very, very simple application. I'm actually using the 5-step process here, which you probably hopefully recognize from last year. Okay, and I got that A is negative 5 meters per second squared. All right. Okay, next example. This one's a little more complicated. Remember those ticker tapes we talked about? Okay, pause the video and really try this one. This will take you a little bit of time to do this, but you really should put some time and effort into doing it before I show you the solution. Okay, so you have 2 different ticker tapes for 2 different moving objects, A and B. Okay, and I'm telling you that 50 dots are made per second, and the dotted lines are a half a centimeter apart. And I want you to figure out the speed and the acceleration of each object. Okay? All right. Well, for A, this is the easy one. Okay? Each dot, the time frame between each dot is 0.02 seconds because there's 50 dots made per second. Okay? And if each dotted line is a half a centimeter apart, then V, which is delta S over T, is going to be 25 centimeters per second. All right? Okay, and in this case, the acceleration is easy. It's 0 because it doesn't change, right? It's a very, very constant speed. Remember, we're talking about speed here, not velocity. All right. So the reason why we can talk about speed and not velocity is because with a ticker tape, everything's going in one direction. Okay. Okay. Now for part B, what I'm going to do is I'm going to divide the data that's given to me into 3 different segments, not equal segments. Okay. For V1, I find that the speed in that interval is 37.5 centimeters per second. In V2, I found that it's 62.5 centimeters per second. In V3, I found it's 75 centimeters per second. So clearly, there's a non-zero acceleration. So to talk about the speed of object B doesn't make a ton of sense because the speed is constantly changing. Now, we can talk about the change in speed, and we need the change in speed in order to calculate the acceleration. In the change in speed between segments 1 and 2, I got 25 centimeters per second. Between 2 and 3, I got 12.5 centimeters per second. And between 1 and 3, which is the overall change in speed, I got 37.5. So V is obviously not a constant, neither is A. The acceleration between segments 1 and 2 is 625 centimeters per second squared. Between 2 and 3, it's 313. But what I'm going to do is I'm just going to take the average. So you can see that it's not a constant acceleration anyway. So the best I can really do, which makes the most sense, is to just find the average acceleration of object B over the entire data set. And when I do that, I get 625 centimeters per second squared for my average acceleration.